Hey y'all! We're going to learn about proportions and similar figures. So, did you know that you can use proportions to find missing side lengths in similar figures? Such figures can help you measure real-world distances indirectly. The symbol squiggly means is similar to. In the diagram, triangle ABC is similar to triangle FGH. Similar means that they have the same angles. So angle B is the same as angle G. Angle A is the same as angle F. Angle C is the same as angle H, but the side lengths are different to each other but proportional. If this one happened to be twice as long, then they would all be twice as long as this one. Aha! Corresponding angles are equal and corresponding side lengths are in proportion. So they're proportional. The order of the letters in which you name figures is important because it tells us which parts of the figures are corresponding parts. So, triangle ABC is similar to triangle FGH, means that angle A and angle F correspond to each other. Angle A is congruent to angle F. Angle B is congruent to angle G, and angle C is congruent to angle H. And we get these ratios. The length of segment AB over the length of segment FG is the same ratio as the length of AC over the length of FH, which is the same ratio as the length of BC over the length of GH. Shall we verify? Let us verify. So the length of AB over the length of FG is 8 over 12. Does that equal the length of AC over the length of FH, 10 over 15? And are both of those equal to the length of BC over the length of GH, 12 over 18? Well, let's simplify each one of these fractions and find out. Let's see, 8 is 4 times 2, and 12 is 4 times 3. The 4's cancel out, and that's 2/3. 10 is 2 times 5. 15 is 3 times 5. The 5's cancel out, and that's 2/3. 12 is 2 times 6, and 18 is 3 times 6. The 6's cancel out, and each one of these values, each one of these ratios is equal to 2/3. Pretty neat, huh? So we can use this information to solve for missing sides. Alright, so triangle ABC is congruent, or not congruent, is similar to triangle DEF. So that means that AB corresponds to DE, and BE corresponds to EF, and AC corresponds to DF. So we want to find out what is the length of DE. Alright, well, then we're going to need to set up a ratio here. We know that BC, the length of BC over the length of EF, is equal to the length of AB over the length of DE, because they are corresponding parts and their corresponding ratios are equivalent. So 10 over this is equal to 16 over 12. Alright, so BC is 16 and EF is 12, so we substitute there, and then AB is 10, and then DE is what we're looking for. Now we can use cross products. 16 times the length of DE equals 12 times 10. Simplify a little. 12 times 10 is 120. Now we need to divide both sides by 16. And we get that the length of DE is 7.5. So the correct answer is A. Bubble it in completely. There we go. Don't leave any blank spaces at all, ever, in your entire life. Alright, pause. See if you got it. Alright, so we want to find out what's the length of AC. Well, I know that AC over DF, or the length of AC over the length of DF, is going to be equal to the length of BC. That's nothing. It was never there. BC over EF, the length of EF. Now I can substitute some things. Just did write a proportion. Now I'm going to do substitute lengths. I don't know AC. I do know DF. So I'm going to change color. So AC over the length of DF is 18 equals the length of BC, 16, over the length of EF, 12. Cross products, 12 times the length of AC equals 18 times 16. 18 times 16 equals 288. So 12 times AC equals 288. Then I need to divide both sides by 12, and 288 divided by 12 is 24. So the length of segment AC is 24 units. Ding! Ooh. I wonder if there was some way that you might learn in Boy Scouts that we could know how tall this building is without being tall enough to hold a ruler up to it, and without having a ruler that long. Indirect measurement. The sun's rays, so here's Mr. Sun. The sun's rays come down parallel, and they cast shadows. And they strike the building and the girl at the same angle, forming two similar triangles. So like her shadow is right here, and then the building's shadow is right here. So how tall is the building? Well, we've got two similar triangles because they come at the same angle, and we just need to set up a proportion. The girl's shadow to the building's shadow is the same ratio as the girl's height to the building's height. So the girl's shadow to the building's shadow is the same ratio as the girl's height to the building's height. So now we're going to substitute. The girl's shadow is 3 feet long. The building's shadow is 15 feet long. The girl is 5 feet tall. The building is how many feet tall? Question. Cross products. 3 times x equals 15 times 5. Simplify. 15 times 5 is 75. Divide both sides by 3. And we get x equals 25 feet tall. That building is 25 feet tall, y'all. So, pause it and see if you got it. All right. There is a 6-foot tall man standing next to a flagpole. So here is a man. He's 6 feet tall. He's standing next to a flagpole. The flagpole is 17.5 feet tall, and the man is 6 feet tall. Let's see, the shadow of the man is 3.5 feet. Here's the shadow of the man. The shadow of the flagpole is going to be a similar, going to form a similar triangle. And what is the height of the flag? Wait, whoa. What did I do wrong here? The shadow is 3.5 feet. The shadow of the flagpole is 17.5 feet. So this is 17.5 feet. And this is our unknown. We'll call it h for the height of the flagpole. So let's set up a proportion. So man shadow man shadow over flag shadow equals man height over flag height. Okay, so man shadow is 3.5 feet. Flag shadow is 17.5 feet. Man height is 6 feet. Flag height is h. So let's do cross products. 3.5 times h equals 17.5 times 6. 17.5 times 6 equals 105. So 3.5h equals 105. Then we need to divide both sides by 3.5. And we get 105 divided by 3.5 is 30. 30 feet tall. So we get h equals 30 feet tall. So the flag is 30 feet tall. Alright, so we got these things in life called scale drawings. A lot of times you look at a map and that's a scale drawing. It has a scale on it. A lot of times you'll see a little scale like this. And then it'll say like 1 mile or whatever. But this is what our scale looks like. Scale 1 inch on the map is 110 miles in real life. And the ratio of length on the map to distance in real life is always the same. And that ratio is called the scale of the drawing. So, what is the actual distance from Jacksonville to Orlandito? Use the ruler to measure the distance from Jacksonville to Orlando on the map. So, let's see, that's 1 inch plus, let's see, this is, right here is half an inch. Right here is 1/4 of an inch. So this looks like another 1/4 of an inch. So that's 1 1/4 inches, which is 1.25 inches. Alright, so map scale is map distance over actual distance. Let x equal the total distance from Jacksonville to Orlando. So, if we do map distance over actual distance, 1 inch over 110 miles equals 1.25 inches on the map over x miles. And now we're going to do cross products. 1 times x is x. 110 times 1.25 is going to be x. So 110 times 1.25 is 137.5. So the distance from Jacksonville to Orlando is 137.5 miles. Pause it. See if you got it. Alright, so the distance from Jacksonville to Gainesville on the map is about 0.6 inches. What is the actual distance from Jacksonville to Gainesville? Well, 1 inch over 110 real miles equals 0.6 map inches over x real miles. 1 times x is x. 110 times 0.6 is 110 times 0.6. So x equals 66 miles. So it's about 66 miles from Jacksonville to Gainesville. You know, I should tell you that your secret code phrase is yellow yolks. Like the yellow yolks inside of an egg. Yellow yolks. Okay, so a scale model is sort of like a scale drawing, except that it's 3-dimensional instead of 2-dimensional. And it's still similar, which means that the ratio of linear measurements are always the same. And the ratio, that ratio that's always the same, is called the scale of the model. So, here is a scale model. It's a giant heart that is 14 feet tall. That's huge. You can go inside of it. See, there's the stairs. Okay, the heart is the ideal size for a person who is 170 feet tall. About what size would you expect the heart of a man who is 6 feet tall to be? Let's set up ratios. The height of the giant heart to the height of a man's heart is going to be the same ratio as the height of a giant person to the height of a guy. So let's substitute. The height of a giant heart is 14 feet. The height of the man's heart is what we are looking for. The height of a giant person, they say, is 170 feet. And the height of the man is 6 feet. Now we can do cross products. X times 170 is 170x. 14 times 6 is, well, they skipped a step there, didn't they? What's 14 times 6? 14 times 6 is 84. So 84 equals 170x. Then we're going to divide both sides by 170. So 84 divided by 170. 84 divided by 170 is about 0.49. So x is approximately equal to 0.49. That's why it's squiggly equal sign. And that means it'd be about 0.49 feet, or about 5.9 inches. How did they get 5.9 inches from that? Remember this. 0.49 feet times 1 foot on the bottom, so feet will cancel. 12 inches on the top. And 0.49 times 12 is, what? Didn't work out. 0.49 times 12 is 5.88, which is about 5.9. Cool, dude. Pause it. See if you got it. Alright, so scale model of a building is 6 inches tall. The scale of the model is 1 inch to 50 feet. How tall is the actual building? So 1 inch of the scale is equal to 50 feet in real life. So 6 inches in the scale model is equal to x feet in real life. Cross product, 1 times x is x. 6 times 50 is 300. So 300 feet. Bada boom, bada bing, bada boing. Wow, we're done again. That's super cool. All right, well, talk to you later. Bye.